So the magnetic field plays a major role in all of jet physics, from launching to particle acceleration to the emission processes. And polarization provides us with a unique tool to study the magnetic field. But on top of that, it might also convey us some information about the gamma ray emission process. We've seen, well, I wanted to say several examples, but actually we just saw exactly this example 3 times by now, I think, where a coherent change in the EVPA, which we call a rotation, coincides with gamma ray flaring activity in the source. And after several occasions of such contemporaneous events were seen, we started the RoboPol program, where we observed a statistical sample of sources for 4 seasons in optical polarization, and we've published a series of papers on that subject matter. One of the key results that we presented is the following. So for each rotation that we identified in our data set, we searched for the closest gamma ray flare, calculated the time delay between the 2 events. And here what you can see is the absolute time delay between rotation and closest flare in the black curve. Now let's assume those 2 types of events are completely unrelated. We can simulate that by randomly placing our detected rotations arbitrarily within our observation time frame. Then we repeat this analysis, and you can see several of such simulation results shown in the gray curves. And we ask the question, how likely is it that one of such simulations lies completely left of the distribution that we got from our real data? And this is rarely happens, just 5 times out of 10,000 simulations. So our conclusion is that the distribution of time delays that we find in the data is unlikely due to coincidence. So the implication, of course, then is that at least some of the rotation events, if not all, have to be physically linked to gamma ray activity. Now, when we deal with EVPAs, we always have the issue of the 180 degrees ambiguity. So for instance, if we have 2 measurements and we get a change of 80 degrees, we can't tell if it's intrinsically 80 degrees or if it was minus 100 degrees or any other addition of n times 180 degrees. So here, as an example, I'm showing one of our best sampled RoboPol EVPA curves on the bottom. And to demonstrate the effect of time sampling or poor sampling, I've removed every second data point. And in this part, you can see the EVPA seems fairly constant now. If we drop every other data point, we lose this one, which I've circled here in red. And suddenly this EVPA apparently aligns to a long rotation larger than 200 degrees. This clearly demonstrates that poor sampling can lead to false rotations. And vice versa, it's also possible that we miss some fast rotations. For instance, one could imagine that this, what started here, continued as a fast long rotation, which we simply didn't cover because we don't have any data points in between. So we wanted to ask the question, how often do we miss to detect rotations? And how many of our rotations are affected by the ambiguity? So in RoboPol, we observed a subsample of our sources for an additional 4th season where we use daily observations. And here on average, we found 0.73 rotations every 100 days in our entire sample. So in the same sample that we observed during our main campaign for 3 years with on average weekly sampling, we just detected 0.25 rotations every 100 days. So the implication is, had we observed this sample with daily time sampling instead of weekly observations, we would expect to have detected 3 times as many rotations as we actually did. So clearly we must have missed probably much faster rotations in our data. The question, how many of our rotations are affected by the ambiguity, is not that easy to answer. In this paper, we introduce a method where we recover the intrinsic distribution of EVPA variability on different timescales from the data that is affected by the ambiguity. So on the shortest timescales, we have fairly small variability in the EVPA, and once we go to longer timescales, the variability increases. So once we've recovered this distribution, we can estimate the fraction of data that would exceed 90 degrees. And due to the ambiguity, if, for instance, we sample with 10 days, we would not be able to detect any variability larger than 90 degrees because of the ambiguity. So in the plot below, I'm showing the fraction of EVPA changes that exceed 90 degrees in this red curve. And for instance, on 1 day time scale, we expect about 4% of the data to exceed 90 degrees. But ROVO was done with a single telescope. The daily sampling was the best we could do for this program. So we couldn't recover any variability larger than 90 degrees. So there's clearly a discrepancy between what we get from the data and what we expect to see. And this is actually the case on almost all timescales. Another thing that we can do with this distribution is to answer the question, how likely is a rotation measured correctly? So this probability is shown here as a distribution over the rotation events that we have identified in the main 3 years of our program. And the lower half, so below 50%, means that those rotations are more likely to be measured incorrectly than they are to be measured correctly. And as you can see, that's actually the majority of the rotation events that we have identified in our data. And those where we are confident that they are more likely correct than incorrect, even in those cases, the probability doesn't go up beyond 70%. So what are the implications for the results that have previously presented regarding the rotation and gamma ray connection? So despite those issues, we've clearly demonstrated that this distribution is not consistent with random associations, and this remains a valid fact. However, now we have to take into consideration that probably half or more than half of our rotations are false rotations. So one could imagine if those are responsible in particular for those long time delays, and we got rid of those, this could strongly increase the significance of our result. So this is something we want to test. And then, of course, we also have missed a lot of rotations, which are not considered in this analysis. And there are far more flares in the data than rotation events that we've detected. So we clearly want to take those into consideration, for which obviously we need better data, better sample data.
3 more minutes.
Okay. So the question is, how much better do we need to do with sampling if we want to go for basically a second RoboPol program with better sampling? So let's take a look again at this plot. So we estimated then that on weekly timescales, which on average we used in our main campaign, 11% of the data exceeds 90 degrees, which we were not able to recover because, well, we're sampling limited. If we go down to daily sampling, this reduces to 4%. So this is a significant improvement. But let's think of this in terms of rotations. So in this plot, again, I'm showing the probability that a rotation is measured correctly for different rotation rates and rotation durations. And in those dashed curves, those are for weekly time sampling. And the first thing to notice is we're not able to detect any rotations faster than about 13 degrees per day, because those, when sampled weekly, will exceed 90 degrees. So we cannot measure those. Once we use daily time sampling, we can measure much faster rotations. And even more importantly, we will be far more confident that we measured those EVPA rotations correctly, especially for slower rotations. So what I want to pitch here is the idea of basically running a second RoboPol program, use the strength of a statistical study, a statistical approach, where we sample a statistical sample of sources, observe it for a long period of time, but this time with a significantly better time sampling. And as I could hopefully demonstrate here, daily observations, which are affordable with a single telescope, provide a significant improvement over what we could, over what we've done before. So I would like to leave with this quotation, and thank you.